Okay, so we are doing the energy notes, and make sure you have your page number. And if you're on a Monday, Tuesday, first, second, or third, actually, if you're just third period, because that's the only STEM physics I have on Monday and Tuesday, you're the 412. If you're fourth, fifth, and sixth, you'll probably see this closer to the 14th. Whatever day you're taking them, they'll give it a date. Doesn't matter. Okay, so we're going to talk a little bit about energy in general, and then we're going to break it down into the forms so we can do the math. So let's talk about the definition. Oh, I could probably spell it right? So energy, just as its own definition, is the ability to change an object or its environment. So that's the general definition of energy. And you have to think that energy is used to change something. An object can be changed or its environment can be changed, and it can be done through several types of energy. So remember that forms of energy sheet that you guys annotated. You want to keep that handy because those are all the different forms of energy that objects can come in contact with. Okay. So let's talk about the conservation of energy. So we've already done a lot as far as work with the conservation of energy, but let's talk about the definition of the conservation of energy. So remember, energy cannot be created or destroyed, only changed forms. So you can only change forms of energy. You cannot create it or destroy it. You can also transfer it from different objects, but once that energy is transferred, if it leaves another object, it goes to another object that was not being destroyed. That means it just was transferred or transformed. Okay, so let's go ahead and talk about those two words as well. So we'll say transformation of energy. So transformation, just think of the word transformation in general. That means to really change. When you transform, you change. So transformation of energy is when energy changes forms. Okay, so it might go from potential to kinetic energy, or even more specifically, we could say, well, it's going from gravitational potential energy, like a water in a dam, and it's being turned into mechanical kinetic energy as it spins the turbines, and then that's being transformed into electrical energy, which we use as electricity. So those are transformations of energy. So that energy conservation gizmo that you guys did, you talked about all the ways that energy was created for us to use as electricity, but remember, it was always transformed from other types of energy, like the dam or the windmill. So wind energy, that spins the windmill blades, which is mechanical kinetic energy, which spins a turbine inside, which then creates electrical energy. So those are all transformations of energy, meaning energy is transformed from one to another form. Okay. We also have a transfer of energy. So in this case, transfer of energy just means energy is moved from one object to another. It can also transform in that transfer as well. So those two words sound alike, like transformation and transfer, but remember, transformation means the energy had to change to a different form. Transfer just means it moved from object to object. So my coffee in my coffee mug that's right here next to me is going to heat up the coffee mug itself, and I might feel that heat. It just transferred from one object to another. Okay. So those are the big vocabulary words to think about while you're doing this. Now, we're going to jump right into the forms of two main forms so we can get into the math. So we've talked a lot about the two forms. The first form is what we call potential energy. So we'll start with that one. And then when we get into the math, there's lots of types of potential energy. Remember, you have gravitational potential energy, you have chemical potential energy, you have potential energy that's stored in elastic, so elastic potential energy. Those are all different types of potential energy. But mathematically, we're really going to talk about one, and that's going to be gravitational potential energy. So gravitational potential energy is going to be the energy due to an object's position, okay? But in general, let's just talk about potential energy in general. That's energy stored in an object. And then mathematically, we're just going to go with gravitational potential energy. So I'm going to write it down, and I'm just going to use PE for potential energy. Remember, your gizmo used U as the variable, but we're going to use PE in this unit as we're doing our math. But do realize U also stands for potential energy. So gravitational potential energy is energy due to an object's position. Okay, so that's like saying, well, my coffee cup, you can hear it, is sitting on my desk right here. It's above the ground, therefore it has gravitational potential energy because it has the potential to fall to the ground. And when it falls, that's going to turn it into kinetic energy. So that stored energy due to my coffee cup being on my desk is why it has potential energy, gravitational potential energy, because gravity would actually pull it downward if the table or the desk wasn't here. So remember, that's a normal force. So my desk is a normal force. So just to think about that, I'm just going to, since you guys can't see what I'm talking about, if this is my coffee cup on the desk and this is the ground down here, so we've got ground and we've got desk, okay? We know that there is a drop for it to fall onto the ground. That height here is what gives the gravitational potential energy to my coffee cup. Now, if I took my coffee cup and I set it down on a stool and moved it, I've just changed the height of it. Therefore, my gravitational potential energy is going to go down because there's less ability.
Eric and Nancy, contact the office. Eric and Nancy, contact the office.
You can tell I'm in class now, right? So now we have announcements coming on the speaker. All right, so ignore that. All right, so gravitational potential energy is what we're going to use when we're talking math. All right, let's go ahead and do the equation. So again, we're going to use PE as the variable. So PE is the variable for potential energy. So PE is going to be potential energy equals, we have our M, we've used this before, mass, okay, I'll put parentheses around it so we remember, times G, we've seen that before, now we're going to use it in the equation, which is gravity, and H, which is height. So remember, height is technically a distance also. So it's the distance from the ground to the top of wherever the object is. So your height is basically a distance. Gravity, remember we've used it a lot, it's an acceleration pulling you downward. And mass is going to be the mass of the object. So let's talk about units then. Because remember, units matter, and units literally follow the equation, which help us understand what units we need to end with after solving a math problem. So in this case, the unit for height, let's start backwards. We've done height before as a distance, so we're going to have that in meters. And we know that gravity is 9.8 meters per second squared. So I'm just going to go ahead and put 9.8 in here because that's a constant. Now in the gizmos, sometimes you'll see them say 9.81. To save us trouble, we just go to 9.8, so there's less digits you have to worry about. And it's meters per second squared, because remember, it's a meters per second per second. So as you're falling, you increase your velocity by 9.8 meters per second every second you're falling. So 1001, 1002, 1003. Each time you change to the next second, you've increased your velocity by 9.8 meters per second. Okay, so that means you get going pretty fast when you're falling until you hit your terminal velocity where air resistance no longer allows you to increase in velocity anymore. Now, if there was no air resistance, you guys would continue to fall at 9.8 meters per second every second until you hit whatever it was that you were falling towards, which is usually the ground. Okay, mass. We've done this a lot of times also. Mass is going to be in kilograms. So let's think of what that gives us. That gives us a kilogram times a meters per second squared times a meter. Okay, so what is that? A kilograms times a meters per second squared times a meter is actually going to give us a kilogram meters squared, because we have 2 meters now, a meters times a meters, over second squared. So that's kind of a long unit. Who wants to say kilograms meters squared per second squared? So instead, they decided to call it a joule. Okay, so a joule, I'll write it out, is a kilograms meters squared per second squared. So we break it down and we call it J, or a joule. And you've probably heard that before in energy. You've probably heard it as a joule when if you've ever like talked about energy before in middle school, or even when we're talking power energy, people will hear the word joule sometimes, which is converted using an equation into watts, which is what you pay for when you're paying your power bill, how many watts you guys use, or kilowatts per hour. Okay, so you've heard watts. Here comes another announcement to interrupt us.
Maconie's, it's in the office conference room. Again, if you've ordered Maconie's, your order is now in
all those teachers
conference room
that ordered Maconie's. I didn't order it because I have to go home soon. So there's a circle. Oops, and I don't know why I made it with a 1, because we have 3 variables on the bottom this time. So it doesn't change anything on how the circle works. Putting a third variable doesn't change it, but we still have M, G, and H. But the same thing works by covering up what you're looking for and writing out the equation with what's left. So the base equation, potential energy equals mass times gravity times height. Well, look, if I cover potential energy because I'm looking for it, M next to G next to H being multiplied. Okay, so that's our base equation. So now flip it around. Let's try to look for height. Maybe I give you the potential energy and the mass, and you know gravity. Gravity always stays the same. You cover up H, or height, you get potential energy on top, mass and gravity on bottom. So what do? It's PE divided by M times G. So you would multiply mass and gravity first, then take potential energy and divide it by that number. If you're looking for mass, same thing. Potential energy divided by gravity times height. So multiply gravity and height, take PE and divide it by that number. Now, since we're on Earth and we stay on Earth, most of the time you're just going to know gravity as 9.8 meters per second. But what if I said, what is the gravity on another planet? Or maybe you're on the moon. I might give you potential energy, height, and mass and ask you to find gravity. So if I cover up G, I get mass times height. I know my finger's too big, but mass times height. Here, I'll cover it up with my pencil. And that means I'll get PE, potential energy, divided by mass times height. And so I'm going to multiply those on the bottom, then divide what's on top and bottom. Okay, so you can find any one of those variables using the circle the same way you guys did in the past. All right, so let's try an example. All right, a 2 kilogram book on a shelf 2.5 meters high. It should be is on a shelf, but I forgot the is. It's on a shelf, 2.5 meters high. Okay, what is the potential energy. And I'm just going to abbreviate it PE for now because that's a long thing to write out. So just remember, what is the PE? What is the potential energy? So we're going to do this exactly like we did all of our previous problems. We're going to underline what we're given, circle what we need, and then solve. So I'm given 2 kilograms, 2.5 meters, and I'm looking for the potential energy. So I'm circling it. Now there is something missing. Notice I didn't put gravity in there. That's a constant. So if I don't say we're on another planet and give you gravity, assume we're on Earth, and we're going to use 9.8 meters per second squared. Do not forget it though. If you forget gravity and you just multiply 2 times 2.5, you're going to get the wrong answer. Okay? So I'm going to write out my variables so I remember. All these are the variables, every part of it. So there's 4 in this case. So I'm going to need my PE, my M, my G, and my H. Since I'm looking for potential energy, that's going to be my X. And remember, joules, a J, is my unit. Okay? My mass is given to me at 2 kilograms. So I'm going to write that in mass. I'm not given gravity, but I always remember it's 9.8 meters per second squared. And my height is 2.5 meters. So now I have them all written out. I can solve. So I'm going to use my base equation since I'm just looking for PE. But if I forgot the base equation, I could cover up potential energy. And I remember it's mass times gravity times height since they're next to each other. So I'm going to just put it into the equation. PE, which is X joules. My mass, 2 kilograms, times my gravity, 9.8 meters per second squared, times my height, 2.5 meters. Now, sometimes you might see me just do parentheses. That's fine too. Okay. However you want to write it, you can. And then you're just going to plug it into your calculator. Since it's multiplying straight across, it doesn't matter which number you plug in first. Okay. I'm just going to do it as I wrote it. But if you did gravity times mass times height, it doesn't matter. Okay. So 2 times 9.8 times 2.5 gives me 49. And remember, it's a kilograms meters per second squared times a meter, or what we call a joule. Okay, so we don't have to say kilograms meters squared per second squared. We say a joule. And there we go. Pretty simple, right? Okay, so let's try another one. This time let's look for something else. How about mass? What is the mass of an object? I'm very creative today on my objects' names. It's just going to be an object. 10 meters high with 196 joules of PE. Sorry, I'm squishing it to the end so I have more space. I'm running out of space on the bottom. So what is the mass? I'm going to circle what I'm looking for of an object and underline what I'm given. 10 meters is the height, 196 joules of potential energy. Again, I'm not given gravity. You have to remember it. Okay, don't forget it. But I still am going to write down my variables. So I need a PE, an M, a G, and an H. Now this time I'm given my potential energy, 196 joules. So I'm going to write that there. I am not given the mass. So that's my X. I know that mass is in kilograms. So I'm going to go ahead and write out X kilograms. Gravity is not given to me, but I know it's 9.8 meters per second squared. Height is 10 meters given to me right here. So I have a different equation this time. I'm now looking for mass. So I'm going to cover up my M in my circle. I get potential energy on top, gravity, and height on bottom. So I'm going to say mass equals, I'm going to write it down so I can remember, PE divided by, what did I say, gravity times height, G and H. All right, so now I'm going to plug in all this into that equation. So M is my mass and it's X kilograms because that's what I'm looking for. Potential energy is on top of the problem, of the fraction. So 196 divided by, or joules divided by my gravity, 9.8 meters per second squared, times my height, 10 meters. So there I did parentheses because when I start putting units and then my dots, sometimes the dots get mixed in too easily and I forget what well, I don't forget, but I don't want it to be confusing for you guys. So I'm putting parentheses around it to remind you you're multiplying, okay? So according to how we do things, you have to multiply everything on the bottom and everything on the top before you do the division. You have to take care of what's on top or bottom of the fractions. Well, on top, there's nothing. It's just a single number, so we're good there. But on bottom, there is something, okay? And it's 9.8 meters per second. So I know that 9.8 times 10 is just going to be 98. So I'm going to bring over 196 joules, and then I'm going to do 98. Now this time I have a meters per second squared times a meter. It's going to give me a meter squared second squared. Okay, so because, and remember I talked about units, so I'm going to show you how that cancels to give us kilograms. Well, how does it cancel to give us kilograms? Let's look. You have a joule on top and a meter squared second squared on bottom. Well, remember, a joule is a kilograms meters squared per second squared. We just talked about it up here. Kilograms meters squared per second squared. So what cancels on top and bottom that's the same? Oh, meters squared second squared. Meters squared second squared. What's left? Kilograms. That's what I need. Okay, now I just have to do the division. So I have 196 and I have 98. So 196 divided by 98 is going to give me 2 kilograms. That's my mass. So that's the mass of the object with all of this important information that we just solved with. Okay, hopefully that's pretty easy for you. Okay, so I'm going to do one more where we look for height. It would be really super great if I could squeeze it in there and not have to go on to the next page, but I don't think I can. So I am going to go to the next page and do one more for potential energy before we move into kinetic energy, which is a tiny bit harder, but I think y'all will be fine. Okay, so potential energy, we're going to do one more. So I'm going to say PE continued. And I might move on to a whole new page for kinetic energy so they don't get kind of mixed up and make it harder. Let's do height. So what is the height of a vase or a vase? Depends on how you say it. With 610 joules of potential energy and 20 kilograms of mass. I should have just said, what is the height of a 20 kilogram vase? But instead I didn't. I made it extra long. Okay, so we are looking for mass or height this time. Okay, so what is the height? I'm going to circle it. I've got my joules of potential energy. I've got my mass. And I'm not given gravity, but I know that it's going to be part of it. So potential energy, mass, gravity, and height are my variables I'm going to look for. I'm given potential energy at 610 joules, so it's going to go up here. I'm given mass at 20 kilograms, that's going to go here. I know my gravity is 9.8 meters per second squared, and I'm looking for height, which is going to be x meters. That's a terrible M, but that's an M. All right, so again, the circle is going to help me. So I'm going to go fold this over just so you guys can see the circle. If I'm looking for height, I cover up the H, and I get potential energy on top, mass and gravity on bottom. Okay, so I'm just going to write it down here so I remember. I'll put it up here. Height equals PE on top, mass and gravity on bottom. So, oops, you can't see what the heck I'm doing. Oops, wrong way again. There it is. Okay, so now I have an equation. I have variables. I'm going to plug them in. So height is going to be x meters equals, my potential energy is going to go on top, 610 joules. I'm going to divide that by my mass times my gravity. So 20 kilograms is my mass. My gravity is 9.8 meters per second squared. Okay, so let's talk about what to do next. We want to multiply everything on top and bottom, but there's nothing to do on top, only on the bottom. So I'm going to say equals, and I'm just going to put 610 joules, move it over since that's staying. And I'm going to divide that by my 20 times 9.8, but I have to do that math first. So I'm going to bring up my calculator. I'm going to go 20 times, you guys can't see it, let's try it again. 20 times 9.8, and that's going to give me 196. Now, if I do the units, it's a kilograms times a meters per second squared. Hey, we've seen that, right? Kilograms meters per second squared. You guys remember that? So we technically are ready, and this is a Newton, if you can't remember. Remember, kilograms meters per second squared is a Newton. We're ready to break down this. So let's write down what a joule is. A kilograms meters squared per second squared. So what can I get rid of? Kilograms on both sides. I can get rid of one of these meters, which then takes away the squared because we're leaving a meter behind, and my second squared are gone. So leaving that meter behind means I am going to have a height, which is a meter. So that's how the units work out. And now that I've done that, I'm going to do the division. So now I do 610, and I'm going to divide that by 196, and that's going to give me 3.1, long number there, but let's just go out to one digit for this, or let's go out to just for significant digits. 3.11. If you put 3.1, it's not the end of the world. 3.11 meters. Okay, so that's how we do the potential energy. So it's pretty basic. It's just have one more variable compared to the other three variable ones, but it's pretty easy in math terms. Okay, so let's do kinetic energy. And like I said, for space, for space, maybe I can fit it in. I think I might be able to fit it in. So we don't have to change pages. I was going to, but now I'm not. So kinetic energy, let's get a good definition for it, is just the energy of motion. Now remember, from your forms of energy, there are lots of types of kinetic energy. We have electrical kinetic energy, mechanical kinetic energy, all the types of movement. We have light, which is a kinetic energy, or what we call radiant energy. We have sound. So remember, sound needs a medium to travel through. So when I tap on the desk, the vibrations of the molecules in the desk produce sound. As I'm talking, my throat is vibrating. I can feel my voice box vibrating, causing sound to come out. And then sound travels through the air molecules and to your guys' ears as you hear me. Okay? So energy of motion, things have to be moving. So let's do the equation. So kinetic energy is going to be KE. All right, so it gets a little more complicated, but don't let it throw you off. Equals 1/2 the mass. So half of the object's mass times the velocity it's going squared. So we're throwing in some more stuff there, some halves and squareds. But if you just sort of follow the process, it shouldn't be too complicated. But it is going to get a little bit more into the algebra when we're dealing with that half and squared. Okay, so just pay attention. Now let's, and I'm going to write it down just since I always do that with the others. So remember, KE is kinetic energy equals mass, 1/2 mass. So just M is mass. So I'm going to put the half there times velocity. V is velocity squared. Just so we remember what those variables actually mean. Put the equal sign a little bit further. Oh, look, another announcement.
Please contact the office. Okay, Mike Sequoia, please contact the office.
I thought it'd be more peaceful to stay here, but now I'm realizing they talk more than my dog and children do sometimes. Okay, so what are the units? Okay, so we have a mass. We already know that. That's a kilogram. We have a velocity, meters per second. And technically, we're squaring that velocity, right? So if I'm squaring, I'm going to put the squared outside. Remember, if I put the squared outside, that means I have to square everything inside in the units. And so it's a meter squared and a second squared. So technically it's going to be a kilograms times a meters squared second squared. Oh, remember we had that already on the last one. That's a joule. So a meter squared second, or kilograms times a meter squared second squared is a joule. Funny thing, kinetic energy is joules and potential energy is joules. And remember, if energy cannot be created and destroyed, the amount of joules of potential energy should equal the amount of available kinetic energy once it falls, like my coffee mug. So we'll talk more about that later. So let's do some math examples. But first, I'll give you the circle. Even with the halves and the squareds, there still can be a circle. Kinetic energy goes on top, mass and velocity go on bottom. Now notice I didn't put in the halves and squareds into here. You can, like if you want to just remember it's 1/2 mass and it's velocity squared, you can put them in there just to remember. But really the variables themselves are what we're moving around and not so much worrying as much about the halves and velocities or the squareds. So when we move them around, we'll move the halves and squareds with them. So if it makes more sense for you to put them in there for sure. And then I'm going to teach you kind of how to rearrange the equation in the first place to make it a little bit easier for you. So I'm going to put in that mass a little bit, or that half a little bit better so you can see it. Okay, so let's try that first example. We'll do a basic one first, just looking for kinetic energy. And then we will look for the other variables, which requires a little more algebra. All right, a person throws a 16 kilogram shot put at 7.5 meters per second. What is, I'm going to squeeze it in here for space. What is KE? Kinetic energy. And then I threw the question mark after the hole. So we're looking for the kinetic energy. So I'm going to circle it the best I can with that hole there. I'm given a velocity of 7.5 meters per second and a mass of 16 kilograms. So no gravity involved in this one. Okay, so don't worry about gravity because we're not having to think about that in kinetic energy. All right, I'm going to write down my variables. Kinetic energy is KE, mass and velocity are the two things that I need along with my kinetic energy. So let's see what I have. Kinetic energy is what I'm looking for. We know that it's X, and we also know that we're using joules, just like in potential energy. My mass is given to me at 16 kilograms, and my velocity is given to me at 7.5 meters per second. All right, we're going to plug it into our base equation because we know since we're looking for KE, remember if you cover up KE, you get 1/2 mass times velocity squared. So I'm just going to leave that as the base equation, and I'm going to remember that I'm going to plug it into this. X joules is KE. I'm going to put my half there. Now, sometimes you might see this half as 0.5 as well, because remember, 0.5 is also 1/2. So if you look up an equation online, you might see sometimes it's 1/2 in a fraction, sometimes it's 0.5. Doesn't change anything as far as like how you multiply. Okay. And I'm going to do my mass. So it's 1/2 my mass, which is 16 kilograms, times, I'm going to do parentheses because I'm going to put in my velocity, 7.5 meters per second, and I'm going to put the squared outside the parentheses. So remember, I told you that because it has to remember to square everything inside, including the unit. So I'm squaring the seconds, I'm squaring the meters, and I'm squaring the 7.5. So don't forget that you have to square everything on the inside, and that's how the units work. So at this point, some of this I can just do in my head. Like I know what half of 16 is. I know that half of it is 8. I could also, if I didn't know what half of it was, I could also multiply it by 0.5. So if I was like, I just don't know. Because maybe it's a bigger number. You could go 16 times 0.5 and it gives you 8 as well. So just remember half and 0.5 are the same thing. that's going to give me 8 kilograms. I'm going to do that first. Now, I also need to square everything first, because remember the whole exponents. You got to do that before we multiply the numbers. So I have to square everything inside the parentheses. So that's going to give me 7.5 squared. So I'm going to do that in my calculator. Now, if I don't have a squared button, remember we did this before, you can multiply it by itself. So 7.5 times 7.5 equals 56.25. And I also have to square my meters, meter squared, and my second squared, because that gives me a kilograms, meter squared, second squared, which is a joule. Okay, so don't forget that. All right, now that I have my 56.25 done, I can now multiply it by my 8. So I'm just going to leave it in the calculator and say times 8. And that's going to give me, oops, put it down here, 450 joules of kinetic energy. So I'm done with that problem. So just remember, half the mass first, square the velocity next, then multiply your two numbers by each other, and that will give you your kinetic energy. Okay, so let's try a second one. Now we're going to look for something different. So what is the velocity of a 28 kilogram object, being creative again, with 650 joules of Ke? So we have what we're looking for, which is what is the velocity. We have our mass given to us, 28 kilograms, and we have our kinetic energy in joules given to us. So we are ready to write down our variables. I'm going to write down the same variables I did before, all of the ones that are in the problem. So I need a Ke. This time I'm given 650 joules. I need a mass. I'm given 28 kilograms. And I also need a velocity, but I'm not given that. So that's going to be x, and my velocity units is meters per second. Alrighty. So now we need to find out our new equation, because we're looking for v this time. So notice here I didn't put the squared, because down here in the variables, because we're going to deal with the squared later once we plug in everything in. So don't worry about squareds and halves when you're writing your variables. Just write them as is, and then we'll plug them into the equation with the halves and the squareds. So my equation, I'm looking for velocity. I'm going to cover up v, and I'm going to get kinetic energy divided by 1/2 mass. Okay, so Ke is on top, 1/2 mass is on bottom. So kinetic energy, I'm gonna say velocity squared. Notice I didn't get rid of my squared though. So I left it over here with the velocity. We'll deal with that later. We're gonna have to deal with it later. Oh gosh, you guys can't see what I'm doing. So I'm gonna say velocity squared equals my Ke over top of my 1/2 mass. Okay, so this is where algebra kind of comes in to help us rearrange the equation to make it work a little better for us. Okay, so that half mass down there can be kind of frustrating, and dealing with it and when to deal with it makes it so sometimes kids don't get it correctly. So this is our base equation looking for velocity, and I don't like to leave the half like that. So anytime you have a fraction on the bottom of an equation, to get rid of it, you multiply by its reciprocal, or 2/1. That cancels out this half on the bottom. So I'm just showing you how to get to the next step. Now, once I do that to the bottom, I also have to do it to the top. So 2/1. So I actually have to multiply kinetic energy by 2/1. Well, we also know that 2/1 is technically just 2. So my new equation from here, without all this mess, I'm going to move it over, would look like this. Velocity squared equals kinetic energy times 2, because remember, I don't need the over 1 anymore. And now I'm going to put that all over just the mass. I got rid of the half. So all I did was multiply it by its reciprocal on top and bottom, giving me a 2 on the top. Now I'm multiplying kinetic energy by 2, and now I don't have to deal with a fraction on the bottom of a fraction, which can be kind of obnoxious and annoying if you don't. Now I still have this squared over here. So technically at the end or in the beginning, before you even start, you're going to have to get rid of the squared by square rooting both sides of the problem. Okay, so to get rid of the squared, I'm going to go square root velocity squared, which is going to give me velocity, equals, I'm also going to square root this whole problem after I've solved everything inside. So that's going to give me velocity equals, make it a little bigger, kinetic energy times 2 divided by mass, square rooted. Okay, so this is where we started. Then we went to here. Now we're at here. And I'll kind of draw a squiggly line so you don't get those two mixed up. So our final thing is going to be right here that we're using. So I know that was a lot of steps. So what you can do is in your notes, just keep it as velocity equals KE times 2 divided by mass, and then square root at the end. That gets rid of the squared on both sides. Remember the a squared plus b squared equals c squared, and we had to square root both sides at the end to get rid of the c squared. You didn't want c squared, you wanted c. Same deal. You don't want v squared, you want v, so you have to square root both sides. Okay? Now I'll tell you, doing this makes it really, really fast. You can just do KE times 2, divide it by the mass, square root, and you've got an answer. So let's plug all this information into this equation. So velocity is x meters per second. So I'm right here. Equals, now I want my KE on the top. So that's my kinetic energy, 650 joules on top, and I'm multiplying that by 2. I'm going to divide that by my mass, which is 28 kilograms. And I'm going to take all of that at the end and square root it. So according to math, you have to do everything inside the square root sign first. So just treat it like a normal multiplication division problem, and then we'll square root it at the end. So the only thing I can do is what's on top is 650 times 2, because there's nothing to do on the bottom since it's just 28 kilograms. So 650 times 2 is going to give me 1,300, because I know that 600 times 2 is 1,200, and 50 times 2 is 100. It's a little Common Core math for you. All right, so 1,300, and it's joules. Since the 2 doesn't have an actual unit, it doesn't matter, because it's just multiplying by 2. So I'm still carrying over my joules. Dividing that by 28 kilograms, because I'm just moving it over, but I'm also remembering to move over the square root. So after I solve this, I can then square root it. I'm starting to run out of time or space over here. So now I'm going to do 1,300 joules divided by 28 kilograms. So 1,300, there we go, divided by 28, that's going to give me 46. Remember, I'm not done though, guys. And it's going to give me 46, I'm going to move it down here, 46 point, let's go 43. Now, a joule divided by a kilogram. Remember, if I break down a joule, it's a kilograms meters squared per second squared. So my kilograms cancel. That leaves me with 46.3 meters squared per second squared. Wait, what? Meters squared per second squared? Oh, remember, guys, we're not done. We still got to square root everything, which will also square root our meters squared and our seconds squared. Because what do we want? Just the meters per second. Okay, so I'm going to take this number and square root it. So I have to flip my calculator sideways. There we go. To get the square root button. So I'll just show you my square root button is right here, the little 2 and the X. So if you forget or you don't have one, let me know. There are some calculators, scientific calculators on Google you can get to. But on the phones, I have to flip mine sideways to see the square root button. So what I'm going to do is plug in, what's my number? 46.43. So 46.43, and I'm going to hit my square root button, and it's going to give me and I'll just go 6.81. Oh gosh, that was a big chunk of lead to break. Now it's out too far and I'm really going to break it. There we go, 6.81. Now I didn't just square root the number, I square rooted the meters and the seconds. So I'm going to get a meter on top by itself and a second on bottom. giving me a velocity unit just like I need. 6.81 meters per second. Okay, so this is the equation number 3 here, the final equation that you want to remember. And if you forgot how I got there, we'll keep practicing it. Don't worry. So we're going to try one more because the format is a little different for finding mass as far as the algebra goes. I have to move it down because I'm going to run into my answer there. Okay, so we're running out of space on my paper, but I'm going to squeeze it in there the best I can. So the last one we want to do is how do we find mass? What is the mass? Holy cow, I'm doing this again. What is the mass of an object moving 5 meters per second with a KE of 100 joules? That's a question mark. That's a terrible question mark. There we go. Try it again. So what is the mass of an object moving 5 meters per second with, that's a W slash if you're wondering, a kinetic energy of 100 joules? So now I'm looking for mass. I have a velocity. It's moving 5 meters per second. I have a kinetic energy of 100 joules. Okay, so I'm looking for mass. And that means I need to rearrange my equation again. So my mass, 1/2 my mass, so I'm going to cover that up. I'm going to get KE over velocity squared. Okay, so I'm not going to get rid of my halves and squareds when I write it down here. I'm just going to still remember 1/2 my mass equals kinetic energy divided by velocity squared. We'll rearrange it like we did up here to make it fit. All right, so in this, before we plug in everything, I want to put down our variables so we have them. KE, mass and velocity, kinetic energy, mass and velocity. So this time we have 100 joules as our kinetic energy. Our mass is not given to us, so that's going to be what we're looking for, x kilograms. And our velocity is 5 meters per second. So I'm not going to plug it in yet because, again, we're at that half. And some people are like, oh, I'll just wait till the end. I'll get my M and then I'll half it. Does not work that way, you guys. You're going to end up with the wrong answer, and I'll prove it to you by showing you. So instead, we're going to get rid of the half in the beginning, just like we did on the last one. To get rid of something, you multiply it by its reciprocal, 2 over 1. We did that at the bottom of the fraction up here, 2 over 1. And so in this case, we had to multiply the top by 2 over 1 since we did it to the bottom. Well, in this case, if you do it on one side of the equation, you also have to do it on the other side of the equation. Multiply by 2 over 1. Well, the 1 doesn't mean anything. So look where we're going with this. The same place we went last time. Kinetic energy times 2. So that's going to be mass equals, so I got rid of the half by multiplying by the reciprocal. Kinetic energy times 2 looks just like the one above, right? Kinetic energy times 2. And this time it's dividing it by velocity squared. I can't get rid of the squared yet. I still have to deal with that squared. But my final equation, this is the one I'm going to use to plug in all my information, is right there. Okay? So mass equals kinetic energy times 2 divided by velocity squared. So if you're wondering, why can't I just do kinetic energy divided by velocity squared and then get the mass and divide it by half? Is because or multiply it by half, is because you'll get the wrong answer. Okay? It doesn't mathematically work. Algebra doesn't work that way. So let's plug in all of this to that. So mass is x kilograms, that's M, equals my kinetic energy is on top, 100 joules times 2. Remember, it's just 2. There's no unit on 2. And I'm going to divide that by my velocity squared, which is 5 meters per second. But here's the deal. I'm going to put parentheses around it so I remember that I'm squaring everything inside. And it's not like some people will put the squared with no parentheses and they'll be like, oh, meters per second squared, it's an acceleration. And they'll forget they had that squared there. They'll just mistake it for the acceleration unit instead of knowing they have to square. So this reminds me that I have to square the seconds, I have to square the meters, and I have to square the 5, all of them. Okay, so according to orders of operation, I have to solve everything on top and everything on bottom. Well, there's stuff to do on both. There's multiplication on the top and there's squaring to do on the bottom. So it doesn't matter which order. I do the top or bottom, doesn't matter, because I'm going to bring them over here and then divide. So 100 times 2, 100 joules times 2 is going to be 200 joules. Simple. Now I'm going to square 5. Well, I can do that in my head because I know 5 times 5 is 25. So I'm going to just do that in my head and say 25. But remember, you're squaring the meters and the seconds. So it's meters squared per second squared. So I can just do this part in my head. 200 divided by 25, because I know that how many quarters are in $2 is 8. So I'm going to put 8. But how did we get kilograms? I know it's 8 kilograms because I know I'm looking for mass. I know that. But how did I get it? Remember, a joule is a kilograms, meters squared per second squared. Meters squared per second squared cancel on top and bottom, leaving me with kilograms. That's how I got my 8 kilograms. So that is the answer for that. It's really pretty simple. But I want to point out, had you forgotten to do that and you just said, oh, I'm not going to use this, I'm just going to half the mass at the end. Well, if you just did kinetic energy, 100 divided by 25, okay, 100 joules without multiplying by 2 and leaving that half. Had I done that, I would have had 100 joules divided by 25, okay? That I know is 4. I'm going to put it in here. Now, if I were to say, oh, 4, and then I'll just multiply 4 by a half, well, what's 4 by a half? That's 2 kilograms. That would have been the wrong answer, you guys, because this half would have had to been dealt with a different way by going 2 over 1 times 2 over 1, giving us actually 8, okay? So if I got 1 half times 4 here, I would have had to gone, 2 over 1 times 2 over 1, and I would have ended up with 8. So don't just wait till the end and say, I'll just half the mass and get 2. Nope, wrong answer. That's not how it works algebraically. So that's why I have you rearrange the equation first by going mass, get rid of the half by multiplying by the reciprocal and bringing the 2 over here, okay? So that they look relatively similar. Kinetic energy times 2 divided by mass, kinetic energy times 2 divided by velocity squared, okay? The only difference is you have to square the velocity here, and you end up having to square root the whole problem on the top one. All right, that is it for the examples. We will practice more, so don't fret.